Okay, if we look at number 11, so 11 says change to logarithmic form. So for 11a, it's 10 to the 5th equals 100,000. That would be log base 10 of 100,000 is equal to 5, because a log is just an exponent. For b, if you have 10 to the negative third is equal to 0.001, that would be log base 10 of 0.001 is equal to negative 3, because this to the this is that. This base to this power is this result. Then if we look at c, it's 10 to the x is equal to y plus 1. Well, that would be log base 10. Well, since a log is just an exponent, the x goes over here because that's the exponent. And that's what we have. This to the this is equal to that. D, e to the 7th is p. Means that log base e, in this case, of p is equal to 7. So that's natural log of p is equal to 7. E would be e to the 2t is equal to 3 minus x. That would be log base e. Well, log is just an exponent, so the exponent goes over here. So this would be e to the this is equal to that, and I'm done. So there is 11. Let's look at 13. So for 13, I'm now changing to exponential form. So if I have log x is equal to 50, that's the same as log base 10 of x is equal to 50. There's an understood 10. So this would be 10 to the 50 is equal to x. So x is 10 to the 50th. For b, it's log x is equal to 20t. Well, again, if there's no log, there's an understood 10. So it's 10 to this power equals that. So 10 to the 20t is equal to x. And so for c, if I have natural log of x is equal to 0.1, what's up? It's log base e of x is equal to 0.1. So it's e to the 0.1 is equal to x. For d, if you have natural log of w is equal to 4 plus 3x, it's log base e of w is equal to 4 plus 3x. So it's this to the that power is equal to that. Just let me know if I need to move.
No, you're fine.
Is equal to this result. And then when we have e, it's natural log of z minus 2 is equal to 1/6. So remember, that's just log base e of z minus 2 is 1/6. Since a log is just an exponent, that is e to the 1/6 is equal to this result. So that's 13. And then we go on to 17. Now for 17, it says find the number. So if you have 10 to the log 3, that's 10 raised to the log base 10 of 3. And you can think of those as canceling each other out in a sense, and you get 3. Another way to think of it is a log is just an exponent, so 10 to what power gets you 3? I raise 10 to that power, and I guess I get 3. And so what is b? B is log 10 to the 5th. Well, that's really understood log base 10. So 10 to what power gives you 10 to the 5th? Well, that would be 5. Again, the log and the exponent cancel each other out in a sense. So that's not math, but that's just a way to remember it. So C, if you have a log of 100, that's 10 to what mystery power gets you 100? And the answer is 2, because there are 2 zeros. D, log base understood 10 of 0.0001. So it's 10 to what power gets you 0.0001? Well, what we did is we had 1 and we multiplied it by 10 to the negative 1. 1, 2, 3, 4 times. So that means it's 10 to the negative 4th. So this would be -4. Okay, and then E is an egg. E is an egg, turns out to be e to the natural log of 2. That's 2, because then again, those cancel each other out in a sense. Natural log of e to the -3rd, that's just -3. And e to the 2 plus natural log of 3. Well, notice if I have an addition in the exponent, that's the same as e squared times e to the natural log of 3. Because with like bases and I multiply, I add the exponents. But what is e to the natural log of 3? That's just 3. So this is 3e squared. 24. So then if I look at 24, it wants you to solve natural log of x squared is equal to the natural log of 12 minus x. Well, if I have natural log of a is equal to natural log of b, I know that a must be equal to b because natural log of x is a 1-to-1 function. So that means that x squared, this stuff and this stuff, must have been equal, right? So x squared is equal to 12 minus x. So x squared plus x minus 12 is equal to 0. Now I have a quadratic that I can solve. Anytime you're solving by hand, you want to get equal to 0. So you're going to get, what, x plus 4, x minus 3. And so either this is 0 or this is 0, which means you get, what, -4 or 3. Either one of those will work when you plug them back in. So you always need to double check to make sure you have an actual solution. So then we go on to number 29. 29 is natural log of x squared is equal to -2. Well, okay, I need to change the form. I know that that's log base e of x squared is equal to -2. So really it's just saying that e to the -2 is equal to x squared. I go from log form to exponential form. But then that's the same as 1 over e squared is equal to x squared. And then you can just take the square root of both sides and you get plus or minus 1 over e. Because you take the square root both sides and don't forget plus or minus. That's 29. Then I'll look at 31. That's e to the 2 natural log of x is equal to 9. That's e. Well, because of property of log, I can bring this up. So that's e to the natural log of x squared is equal to 9. But then e to the natural log of stuff, those cancel each other out in a sense, and you get x squared is equal to 9, which means x is equal to plus or minus 3. Now notice, if you try and plug that into the original, cannot take ln of -3. So x equals 3 is the only solution. I'm going to be careful with that. So then I look at 33 and I have ex natural log 3 is equal to 27. Well, I want to change the form. I know that I can pull this x up and get the natural log of 3 to the x. Why did I do that? Because now I have e to the natural log of stuff, and I know that this e and this natural log cancel out in a sense. So that's why I pulled that x up. So you get 3 to the x is equal to 27, but I know that 3 to the third is equal to 27, so that is your answer. So that's 33. What about 55? If I go over to 55, it says we start off with Q0 milligrams of radium. And it says that that's our initial amount of radium. And then Q equal to Q0. So Q equal to Q0 2 raised to the -t over 1600. And then they want us to solve for t. So one thing you'll notice in here is when you put in, if the initial amount was 1,600, when I put in 1,600 over 1,600 is 1. So that's when we'll have -1 is in 1,600 years. So that means in 1,600 years, it will cut this thing in half. So t is time in years, and q is radium in milligrams. Okay, I think it's important to label all of our variables. So the main thing for this question that we need to do was to take this thing and solve for t. So first thing I'm going to do is divide and get 2 to the negative t over 1,600. Well, then I want to be able to pull this exponent down. So I'm going to take the natural log of both sides. So q over q naught. Q over q naught is equal to 2 negative t divided by 1,600. Well, then that allows me to pull the negative t over 1,600 down front. And then I can divide. I get this over q naught divided by natural log of 2 is equal to negative t over 1,600. And then that just means that t has to be equal to negative 1,600 natural log of q divided by q naught over, let me make that a little bit nicer. So negative 1,600 natural log of q divided by q, oh my gosh, that was just bad. Q naught all divided by natural log of 2. Okay, so that's 55. Then when you're looking at 56, if you've got q is equal to k to negative t over 5, k is constant, q is bismuth, disintegrates according to, we will say that this is milligrams again. So that means that this is K is a constant. Well, K is probably the initial amount, right? That's actually, note, that's probably Q naught, just so you know. But what they want to do is they want you to solve for T. So when you do, you're first going to divide. And you can either think of it as turning it into exponential form, so you could do log base 2, or to make your life easier, you can just take the natural log of both sides. And you can do that. This is okay because natural log of x is a function. So if my two inputs are equal, then my two outputs must be equal. What does that allow us to do? Well, that means that this constant, I can bring it out front. And so you get negative t over 5 ln 2 is equal to ln q over k. So that means that ln q over k divided by ln 2 is equal to negative t over 5. And just like last time, that means that t is equal to negative 5 ln q over k divided by ln 2. So that's 56. Let's look at 58. So 58 says that q is equal to q naught e to the kt, a classic exponential growth, where q is charge. I don't know what the units are, and q naught is the initial charge, and k is just some constant, right? So if they want you to solve for t, well then first thing I'm going to do is I'm going to divide both sides and get this. Then I'm going to take the natural log of both sides, which I can do because natural log is a function. So you get natural log of Q over Q naught is equal to, and now the reason I did that is so I can pull this constant out front. I get KT, a natural log of E, but the natural log of E is just 1, because I have that memorized. So T is just a natural log of Q over Q naught divided by K. So that's 58. Then we look at number 69, which says I've got elephant growth. Its W is equal to 2600, 1 minus 0.51 e to the negative 0.075 t, all that crap cubed, where W is weight in kilograms, and T is age in years. And it wants to know what is the weight at birth. So part A is, it wants to know the initial weight, which means T is equal to 0. So W is equal to 2600, 1 minus 0.51 e to the, well, that's going to be 0 when you multiply it out, cubed. Well, e to the 0 is just 1, so that's 2600, 1 minus 0.51 cubed. Well, that's 2600 times, I guess that would be 9 gets you to 60, and 4 gets you 100. So that's going to be 2600 times 0.49 to the third. Okay, thank you for not typing that in. 2600 times 0.49 to the third. And that's going to be approximately 305.9 kilograms at birth. And then part B, it wants to know, estimate the age of a female weighing 1,800 kilograms. So first, it gives us this little graph. Give me 1 second. I need to turn on the lights in here and turn on the heat. It's about 1 billion degrees up in here. Turn that down. Okay. So first, it gives us a graph. So if we do it using the graph, we just simply need to look at my phone. Yeah, you're just gonna have to roll with it. Boop. Okay. So if I use that photo, so if we do it from the graph and I crop, then I want to know what happens when this thing is equal to 1,800. So maybe 1,800 is about here. So that's weight equal to 1,800. It looks like the associated y, it looks like it's about 20. So how am I going to do that algebraically? So it seems like when we plug in 20, we get a weight of 1,800. So if that was that one, then the last one is 75. So 75 says, how does population affect walking speed? Well, if S is equal to 0.05, 0.86 log of P, it's a plus. You're going to see, what's up? If you graph this thing, let me go over here to Desmos. Desmos, I need 0.05. So I'm going to do 0.05 plus 0.86 log. Hello, functions. We go log, join sorts, log of X. I think it's pretty clear that as time goes on, that thing is just going to get bigger and bigger. So as your walking speed gets faster, the other changes in that way. What's up? So I'm going to do, let me go here, here. So as P goes to infinity, so it gets larger, it seems like, ooh, walking speed goes to infinity. So as population grows, walking speed increases. Speed increases. Excuse me, and then for what population is the average walking speed? 5 feet per second. So 5 is equal to 0.05 t plus 0.86 log of p. Whoa. There's no t here, sorry. It's just 0.05. 0.05. So that's going to be what's up? 4.95, 0.86 log p. So it's going to be 4.95 divided by 0.86. It's equal to log p. So that really tells you, notice that that's in log form. There's an understood base 10. If I put it in exponential form, it's 10 to the 4.95 divided by 0.86 is what the p is going to be. So I'm going to do 10 raised to the 4.95 divided by 0.86, and I get approximately 569,920 people. Yeah. People is population that gives the walking speed we want. So in the very least, that many people. Awesome.